For years, astronomers have been unable to find up to half of the matter in the universe. The missing baryon problem put into question our understanding of the physics of the Big Bang. We may just have solved it. Fingers crossed. Our astronomical surveys have revealed an observable universe full of hundreds of billions of galaxies, each of them with as many stars. The shining light of these stars illuminates or is conspicuously absorbed by gas and dust within those galaxies. When we extrapolate our observations to the entire observable universe, we find 1 billion trillion suns worth of mass. However, we've known for some time that around 95% of the energy content of the universe is in dark matter and dark energy. This dark sector doesn't interact with light in any way and so is invisible to us. The remaining 5%, the light sector, represents all of the regular matter in the universe. Yet what if I told you that all of the stars and galaxy clusters only comprise 10% of the light sector? The rest has proved as elusive as the dark sector. We think it must exist as extremely diffuse gas in between the galaxies. Yet our intense searches miss up to half of it, at least until now. First, a quick refresher on dark matter and dark energy. And there's plenty more detail in some previous episodes. Dark matter is believed to be an invisible stuff that interacts only through gravity. It comprises 80% of the mass of the universe, or around 25% of its total energy content. Its gravity holds galaxies together and governs the growth of large-scale structure in our universe throughout cosmic time. Now, where dark matter pulls, dark energy pushes. It's anti-gravitational and causes the expansion of the universe to accelerate. This energy of the vacuum comprises 70% of the universe's energy content. The remaining 5% is regular baryonic matter. By the way, a baryon is a 3-quark particle like a proton or a neutron, but really baryonic matter refers to atomic matter. It's the stuff of stars, planets, gas, dust, you, me. Baryonic matter interacts with light, so we can search for it by scanning the electromagnetic spectrum. Except by doing so, we miss most of it. This is the missing baryon problem. There's a huge discrepancy between the amount of baryonic matter our surveys find and the amount that our theories say should be out there. And those theories are pretty solid. For example, in the first several minutes after the Big Bang, hydrogen fused into deuterium and helium. The proportion of hydrogen that ended up getting fused is very dependent on the density of that hydrogen, so the baryonic mass. Measuring the relative abundance of helium and deuterium today tells us that there should have been 10 times as much hydrogen to start with than we actually see today in galaxies and clusters. The second way to calculate the expected baryonic mass is with the cosmic microwave background radiation. Perhaps you remember this stuff. It's the light released at the moment the first atoms formed, nearly 400,000 years after the Big Bang. We still see that light today, travelling to us from distant parts. It carries with it a map of the structure of the cosmos from those early times. These speckles are fluctuations in density that would later collapse to become the galaxy clusters. And by analysing these fluctuations, we can figure out the relative abundance of baryons to dark matter. See, before the photons of the cosmic background radiation were released, they were trapped in the searing hot plasma of baryonic matter. The interplay between baryons and photons resulted in density oscillations, much like sound waves rippling outwards from high-density regions. These baryonic acoustic oscillations helped produce a smaller family of speckles compared to the largest blobs on the CMB map. Those large blobs are driven by dark matter, which doesn't interact with light, so it can't produce density oscillations. By analysing the distribution in speckle sizes in what we call the CMB power spectrum, we can find the relative amount of baryonic versus dark matter. Again, we calculate that there should be way more baryonic matter than we see in galaxies. Following the release of the cosmic background radiation, gravity continued to do its work and collapse these faint fluctuations into gargantuan clusters of galaxies. Supercomputer simulations reveal the shape of this large-scale structure that should result from this gravitational collapse. It's the cosmic web. Rivers and sheets of dark matter flow into giant dark matter halos, dragging baryonic matter with them. In the nexuses between filaments, matter is dense enough for galaxies to form. Our surveys of galaxies confirm that this is what the large-scale structure of the universe looks like. And yet, when we add up the mass from those galaxies, most of the baryonic matter predicted by our theory is missing. So where is it? Well, our best guess is that it's in the form of a very diffuse plasma, atoms stripped of their electrons in between the galaxies. Now, some of that stuff we can see. If the plasma is hot enough, then it emits detectable X-rays. We typically see that stuff inside galaxy clusters where the plasma is relatively dense and is energized by the light of the galaxies themselves. On the other hand, if the material is cool enough, then nuclei can recapture their electrons and become a gas instead of a plasma. This cool gas then absorbs signature wavelengths from light that passes through it. Absorption features in the light of distant quasars reveal this gas lurking between clusters of galaxies. However, by looking only at the hottest or the coolest material, we don't find nearly enough of it to account for the missing baryons. It seems that the missing material must be in the intermediate temperature range. It must be hot enough to still be a plasma, otherwise it'd produce absorption features, but it can't be so hot or dense as to emit detectable X-rays. This tells us that the best hiding place for the missing baryons is the giant filaments that form the cosmic web, stretching in between galaxy clusters. That material would be cooler than the clusters themselves, but should at least be hot enough to form a plasma. See, the vast tidal effects of nearby galaxies create shocks that can heat those baryons to hundreds of thousands or even millions of Kelvin. At the same time, this stuff is expected to be extremely low density, only around 10 times that of intergalactic space. That makes it a more perfect vacuum than anything we've created in a lab or even exists in the Milky Way. And yet those filaments are vast, tens of millions of light years long, and so those solitary baryons could add up to more mass than all of the galaxies in the universe. So, how do we spot this stuff? 2 research groups have figured it out. The secret is the thermal Sunyaev-Zel'dovich effect. We talked about the kinetic SZ effect in our episode on dark flow. The thermal SZ is similar, and again, it makes use of the cosmic microwave background. As photons from the CMB pass through a giant filament, the hot plasma in the filament grants it a little energy boost. In fact, the electrons in that plasma scatter CMB photons to higher energies. So if there's enough of this stuff, then the CMB map should be slightly hotter directly in between galaxies that are connected by filaments. And it turns out it is hotter. 2 teams, Grafen collaborators and Tanimura and collaborators, just published the results of their attempts to look for the Sunyaev-Zel'dovich effect. They both used the latest Planck satellite CMB map in the presumed locations of large-scale structure filaments, which they assumed was between pairs of nearby massive galaxies, the type typically found in giant dark matter halos. It wasn't an easy experiment. The SZ effect is tiny, and so the researchers needed to add together the results from many galaxy pairs. Graf et al. Used 1 million galaxy pairs, while Tanimura et al. Used 260,000. Both teams report detection of the thermal Sunyaev-Zel'dovich effect with around 5 sigma significance. Or to translate, they found the baryons. These filaments seem to have enough of this hot diffuse plasma to match the amount expected from the models. we're a very important step closer to accounting for all of the missing baryons. And this is actually a huge relief. If our predictions for the relative mass in baryons versus dark matter was so wrong, then it would mean that our understanding of the physics of the Big Bang was seriously off. So it seems that most of the regular matter in our universe is spread out in the vastness of intergalactic space, still flowing with rivers of dark matter into the galaxy clusters. As those baryons fall into the dense nexuses of the cosmic web, they'll feed galaxies with material to form new stars. In fact, this verifies that the epoch of star formation in our universe is far from over. In fact, it's only just beginning. The stuff of countless future solar systems is still riding the cosmic web, falling in from the darkest reaches of space-time. Last week we talked about virtual particles, zero-point energies, and the nature of nothing. You guys had something to say. Michael asks whether space containing an intrinsic energy also means that it has intrinsic mass. Well, the answer is, as Gareth Dean put it, sort of. A non-zero vacuum energy would have a gravitational effect, but if it's exactly the same everywhere, then there's no net attractive force. Yet it would still push the universe towards positive spatial curvature, so enough vacuum energy could result in a closed rather than infinite universe. And rather differently to regular matter, vacuum energy doesn't dilute in an expanding universe. This leads to the unintuitive result that it acts repulsively, accelerating expansion. And this is, of course, what our universe is doing. Check out our dark energy playlist for details and tune in next week for even more. Jeremy Zamboli asks whether the annihilation of virtual matter-antimatter particles would introduce energy into the universe and therefore violate the law of conservation of energy. Well, no, the energy is borrowed from the energy of the vacuum for the minuscule time allowed by the uncertainty principle. On particle annihilation, it's given back without producing a real photon. Jeremy also asks if virtual particles can travel faster than the speed of light, can't they escape the event horizon of black holes via Hawking radiation? Well, actually, it's going to take us a few episodes to properly answer that, so just stay with us. TS1336 was expecting last week's episode to be about the discovery of gravitational waves from merging neutron stars. Don't be silly, TS1336. We like to release our episodes on new LIGO announcements at least a month before the announcement. Check out our September 13th episode. Elleran Cohen suggests that instead of presenting lame theories, we should travel 1,000 years into the future and bring back exact answers. We already do that. Where do you think we get all of this stuff? Unfortunately, there's still no theory of everything in 1,000 years, and still no flying cars, would you believe? Waste of time. Next season, we're going to try 10,000 years. Maybe we'll at least get some evidence for string theory or something.